Now that you've given this one a try, let's come up with a plan here on how to finish this problem. Okay. So again, our goal is to find the height of the flagpole. Well, based on the two right triangles that we have here, we will probably be able to find the heights of these right triangles. So in other words, maybe I can find and maybe I'll use the line tool. But maybe I can find from the top of the flagpole to the bottom of the building. Okay. And maybe we'll call that, let's just call that one maybe Z. Okay. And there's another one, right? We also have this length here that we should be able to find. And maybe let's call that one Y. There we go. All right, let's begin with, how about Z? Okay, so this is the bigger angle, the 63 degrees. You can see Z is the opposite side, and this 330 is the adjacent side. So it looks like tangent again. So tangent of 63 degrees should be equal to Z over 330. And if we solve for Z, we get Z is equal to 330 times tangent of 63. And we can do the same thing for Y here. So we have tangent of, and you can see the angle is 53 degrees this time. And the opposite side is Y, and the adjacent side is 330. And if we multiply both sides by 330, we get Y is equal to 330 times tangent of 53 degrees. All right, and so to get the side length that we want, right, if you just do Z minus Y, you'll get that. You'll get the flagpole here. Maybe we should give the flagpole's height a name. Let's maybe call its height X. So if that's the case, well, X is equal to Z minus Y. And if you plug both Z and Y into your calculator and subtract them, we should get approximately 209.7 feet. Moving on to our next example. An object is attached to a coiled spring. The object is pulled down 8 centimeters in the negative direction from rest position and then released. Write an equation for the distance of the object from its rest position after t seconds, given that the amplitude is 8 centimeters and the period is 2 seconds. Okay. One thing I want to point out before we go any further with this problem, and that is when we're doing these types of problems, so maybe I'll write that in these types of problems, we will ignore the effects of air resistance and friction. Okay. So what this means is if you were to say take this mass, pull it down 8 centimeters, and let it go, it is going to, and this is just going to be a very rough sketch. We'll come up with a better one here in a second. That height is going to keep going up to the same height. That wasn't very good. Yeah, it'll keep going up to the same height, back to equilibrium, and then it'll go down by that same amount, and then back up by that same amount, and it's going to keep doing this, right? This is going to look like a sine or cosine graph. Now, if we did want to actually include air resistance and friction, this is actually not going to be that much more complicated, okay? So if you take maybe differential equations with me one day, or take some physics, you'll get to see maybe what this looks like. Okay. All right, so let's see if we can figure out what to do here. Okay. What we're trying to do is describe this situation using a sine or cosine function. Okay. Let's maybe take some of this information here first. The amplitude is 8. So right off the bat, we can say A equals 8. We're also given the period. The period is 2 seconds. Okay. So this thing should, let's say for instance, we had pulled it down the 8 centimeters. If you release it, it should go up and then back down in 2 seconds. Okay. Let's see what that might look like. So we know that the period is supposed to be given by 2 pi over b when we're dealing with sine and cosine. And so we'll just solve for b here. You could multiply both sides by b. And so this must mean that b is equal to pi. All right, so we have a, we have b, and let's think about this a little bit now. Okay, I'm going to actually sketch in a set of axes here to help us out. And we'll call this axis T, and maybe this one up here we could call it H. Why don't we do that? H for height, T for time. Okay. Now, let's think about where we're going to begin, and that should be at the bottom here, right? The way that we're starting this problem is we pulled down that weight, and the moment we release it, that's when we're starting to record the height, okay? So at that moment, we should be at the very bottom here. Okay, let's say that is about right here, say -8. Okay. And remember, because we're ignoring air resistance and friction, that means that this block is going to go all the way up 8 units as well. So it should go all the way up to here. And I just want to sketch in where we're starting. Again, we're starting right here. So if this is going to be some trig function, my question to you is, which trig function would it be easier to write the equation of this curve with? Okay. And you might already have the answer. If we're starting at the bottom of the wave here, it's going to be easier to work with cosine. Okay. And because, right, sine starts at the middle of the wave. Okay. But you may be noting, well, cosine doesn't start down here. It starts at the top. Well, to fix this, all we need is a negative sign in here. So I'll have negative, cosine, and problem solved. Okay. The only other thing I need to do here real quick is put that 8 here, right? Our amplitude was supposed to be 8. Okay. We know B is pi, And you know what? We used h instead of y. Why don't we just replace that with a h? Okay. And we were using t for time, so I have pi t. And now we didn't have to shift cosine over at all, right? If you just put that negative in front of cosine, you make it start at the bottom of the wave. So there was no phase shift. And the center of the wave, you can see, is along the x-axis. So we haven't been scooted up or down either. So C and D are both 0, and this is the equation that we were looking for.